So we said the thing about the imaginary numbers is we can't place them on the number line, but we still want to represent them visually. So how do we do it? We've got this thing called the Argand diagram, and it looks like this. Very familiar, hey? Looks just like the number plane, which works out really good for us. X-axis and Y-axis, although technically when we're talking about an Argand diagram, the X-axis becomes the real axis and the Y-axis becomes the imaginary axis. But don't panic too much. If you label them X and Y, everyone knows what you're talking about, so it's not a big deal. So if I wanted to plot 2, well, it's a real number, so it would go on the real number line, or as we're now calling it, the real axis. It would simply go there. If I wanted to plot something that's purely imaginary, then I'll go on the imaginary number line. I'll plot it down there. And by the way, notice when you're labeling the imaginary axis, there's no I on it. So remember, Y is a real number. Okay? The fact that it's the imaginary axis is telling us it's 4I or whatever. Well, what happens if it's a bit of each? Well, then, just like coordinate geometry, we just plot it in the appropriate spot. So this one would be -2 in the horizontal direction and +1 in the y direction. So we plot it there. 4 minus I, we'd put down there. 4 plus I. And this brings up the first visual piece of information. See, 4 plus I and 4 minus I are, of course, conjugates. So what we should see is conjugates will always be reflected in the real axis, because their real part's going to be the same. It's just the imaginary part's changing from positive to negative. What about if I was to take the negative of 4 minus I? What would happen there? End up over there. So -4 plus I. But again, visually have a look at what's happened. Opposites, or multiplying by -1, so opposite signs, end up being rotated 180 degrees. Or another way of thinking about it, it's been reflected through the origin. Which brings up a really useful one. If we just multiply by I, so if I was to multiply 4 minus I by I, I'd get 1 plus 4I. If we were to multiply by I, we'd end up there. Now visually what ends up happening is it's a rotation of 90 degrees. Now if you think about it, that makes sense, because we just said rotated 180 degrees is when we multiply by -1. So we've multiplied by I, then we've multiplied by I again, so I squared, which was -1. So every 90 degree rotation is a multiplication by I. The wonderful thing about this, of course, is there's a unique position for every number. There's only one number that could go in that spot. This now brings up the idea of locus or locus, however you want to say that word. Horizontal and vertical lines then. So let's look at those to start off with. There's a horizontal line. If we were talking about coordinate geometry, of course, we would just call that the line y equals some constant number. That's still its equation. But if we wanted an equation for that now in terms of complex numbers, what they all have in common is that their imaginary part is all C. So instead of saying y equals C, we can say, oh, well, the imaginary part is equal to C. And we'd have a similar one for vertical lines. On that one, the real part would always equal K on that one. Circles, there's a circle, just in case you didn't recognise. Well, how can we write this? We know a circle is x squared plus y squared equals the radius squared. But we've now also seen that a number times its conjugate will be x squared plus y squared. So we could write this as z times z conjugate is the radius squared. What's this going to be then? Z plus 4 plus I times the conjugate of z plus 4 minus I is equal to 49. So you look at it, you're not sure. I've manipulated it because it's going to be easier for the substitution. So z times z conjugate, and so on. Eventually I can substitute in, but you see I've got things like z times z conjugate, which I know is x squared plus y squared. Z plus its conjugate is twice the real part. So I end up with 2x there, but times 4 is 8x. You might find it easier to sub in x plus y here. Up to you how you do it. But eventually we end up with this equation, which we recognise to be, and it shouldn't be a big surprise because it is under the heading of circle. Oh, it turns out to be a circle. Let's just work out what it is. So we complete the square on it. Something interesting happens. What do we got? We got, it's a circle. Its centre is at -4, -1. Hang on, what was the equation again? And the radius is 7 units. So when it's in this form, it's sort of like we've got the basic one and we've just shifted it. So if you ever see z minus a complex number, but then in the other parentheses you've got the conjugate of z minus the conjugate of that number, you know you've got a circle centre at that number. You just got to be careful. Radius, like normal though, 49 is 7 squared, so the radius is not 49, it's 7. Whoa, what about this one then? 1 on z plus 1 on the conjugate of z is equal to 1. Let's play around with that one. Multiply by z conjugate. Yeah, I think I'll just substitute into that, did I? Yeah. So z conjugate plus z is 2x. Z conjugate is x squared plus y squared. Oh, there's a surprise under the heading of circle. We've got a circle. Ends up being x minus 1 squared plus y squared is equal to 1. So we have a circle. Centre 1 naught, radius 1. Or is it? You see, you would think that's it. But remember, I've rearranged the original question. So yes, that would be the locus for the second line. It is not the locus for the first line, because you can't have 0 on the bottom of the fraction. Therefore, the point 0, 0 does not work. So I've got to exclude it. So we have a single point excluded there. 1C.